All right, so we're going to go back here and do a little bit more work with the definite integrals as limits. One of the things that we really need to practice, and this will come up more in typically the multiple choice section, of where they will give you a limit that you have to then match to a definite integral. It's very similar to what we did with the limit definition of the derivative, in that as you're in the multiple choice, you will think that you're calculating a limit, but what you're supposed to be recognizing is that what you have there is the limit definition of a derivative, and actually using the shortcut rules for derivatives in order to do the limit instead of doing limits. And so the same thing is going to come about with the integrals. Since these limits of sums are definite integrals, and eventually, very shortly, probably the next packet that we have after this, is going to be a shortcut for how do we calculate definite integrals instead of estimating them with Riemann sums. So what we want to do is we want to be able to translate from one to the other. So we're going to revisit that in this set of notes. All right, so what we're going to do here is we're going to first take a look at an example that we're going to remind you what we were doing with the Riemann sums, but then we're going to work on working toward a more general idea of how this works. So for our first one here, write but do not solve an integral expression that would give the area under the curve, and again, I'm stressing that this is net area under the curve, from for the function f of x equals cosecant of x, but from 1 to 3. So we're going to write it as a definite integral. So that definite integral represents our limit of the sum of the rectangles. We're going from 1 to 3 because that's the interval of interest. Our function is cosecant of x, and then our width is our dx. So remember that kind of as you're doing this in your Riemann sums, that the definite integral is the limit of the sums of the rectangle areas. The quantity over here is representing the areas that we are summing up, and the cosecant of x is the height, while the dx represents the width as we are working through this. So, and again, right now, integration of this function is challenging. So we're going to estimate, okay? We're going to estimate using a right Riemann sum. We're going to have 4 equal subintervals, so n is going to equal 4, and we're going to do that to approximate the area. So the first thing, what would be the width of each rectangle, and how do you know? So the formula that we want to just basically memorize for delta x, when you have, and again, we're going to stress on this, that this is 4 equal subintervals, 4 equal subintervals. So when the subintervals or the rectangles are of equal width, we always use this b minus a over n. So for this problem, that's going to give us 3 minus 1 over 4, or 1/2 is our width for each one of these. All right, so the width of the rectangle of the 4 that I have, since it's equal widths, we would have 1/2, 1/2, 1/2, and 1/2. Now, the idea that we have here is that we're trying to basically come up with general formulas for things like our right endpoint. Now, remember, we started at 1, and we're going to 3, but we want the right endpoint. So even though the a value, okay, is going to be 1, when we start that, we're not going to use a equal to 1 as x because that's the left of the first rectangle. We know that the right of the first rectangle is going to be exactly 1/2 later, so 1 plus 1/2, or 1.5. And so that would be the right endpoint of the first rectangle. Now, to get the right endpoint of the second rectangle, we have to add another 1/2. It's going to end up being at 2. The next one would be at 2.5, and the last one would be at 3. Now, kind of working my way toward a generic formula to help myself out here, putting it back in terms of a and delta x, which is my 1/2. that really to get all the way to 2, I did 1 plus this 1/2 times 2 because I was on the second rectangle. And then I did 1 plus 1/2 times 3 to get to the third rectangle. And then 1 plus 1/2 times 4 to get to the fourth rectangle. And so that's kind of the idea that we're looking at, is to get this generic formula. So I'm actually going to jump right down here and where it says look at the third column of your table. And when it says write a rule, I've been trying to help you out in terms of how would you write a rule for that. But we want it in terms of the rectangle number. All right, so we're going to call the rectangle number I. The width of the rectangle, we're going to call that delta x. And then the lower bound, of course, is going to be your A. So my formula for the right endpoint is going to be x sub I is going to be equal to, you always start with your first value, your lower bound. So start with the A. And then each time we went, notice we added as we went the width to move over to the right side. And for the first rectangle, I had to move over 1 width from the start. For the second rectangle, I had to move over 2 widths from the start, and so on. So it'll be A plus delta x times the I. And so that gives us a nice little generic formula for that. And so we do want to kind of pay attention to this. And I will say that in the AP, our favorite, or their favorite, not necessarily, it's actually my favorite too, because the right endpoint is actually the easiest to calculate, that the right endpoint formula is the one that you need to memorize the most. And so I'll even put a little, I'll really emphasize this right here. Now remember, once we had our endpoints that we're going to plug in to get our height, okay, so our height right here, and this was of course my width. So my height was found simply by plugging that into the function. Now my function was cosecant, so it'd be cosecant of 1.5, cosecant of 2, cosecant of 2.5, and cosecant of 3. Now we'll assume that you can type these into your calculator and get the decimal values for it. And then remember that the area of the rectangle is going to be your width times your height that we just had there. So that's going to be our delta x times f of xi. And so for this one, it's going to be very straightforward. The width was 1/2, and then just multiply times our height. And then we would, of course, add that up. And then if I were to add these up, this sum would be approximately the net area from 1 to 3. All right, now knowing that you can get a better estimate by using more rectangles, we're going to do the right Riemann sum again, but we're going to use n rectangles instead of 4. So what happens to your delta x each time if I don't set what n is? You're still going to have that b minus a over n, or 3 minus 1, but we're not going to put in a number where the n spot is. We're going to leave it as n. So my delta x is now going to look like 2 over n. And notice kind of up here, we're kind of building down here to kind of a main point of what this is going to look like. So for this problem, a generic delta x would have been 2 over n. For this problem, a generic right endpoint would have been 1 plus, now it's going to be 2 over n times I. So I'm going to shade that down for this problem. So those are kind of some things that when you start matching them, that we're going to have to look for kind of relationships between parts of the summation and how it matches and helps us locate A, B, what our function is, and where the delta x is on that. All right, so now coming down here, kind of working towards this more general formula, now our equal widths of the rectangles are going to be 2 over n for each of those, all the way down to 2 over n. Right, and then we get down to our x, which is our right endpoint, right endpoint. All right, and so our first right endpoint was 1 plus 2 over n. Our second right endpoint was 1 plus 2 over n times 2. Our third right endpoint was 1 plus 2 over n times 3. And so on until we get to, at the bottom here, we'd have 1 plus 2 over n times n, which actually ends up being equal to 3 for this problem as we go down. Now, and again, our plug and chug here, we would just do cosecant 1 plus 2 over n, cosecant 1 plus 4 over n, cosecant 1 plus 6 over n, all the way down until we get to the cosecant of 3. And then our area of our rectangle, and remember that's going to be our f of x of I times delta x, ends up being cosecant of the 1 plus 2 over n times 2 over n. Cosecant of 1 plus, whoops, times 2 over n. Cosecant of 1 plus 2 over n times 3 times 2 over n, up until we get to cosecant of, and again, if I simplify this all the way down, but I'm going to leave it as 2 over n times 2 over n, because I want to make a kind of point about this. And the point that I want to make is, how would we write an integral with a Riemann, like the Riemann sums, the summation notation versus the integral notation? Now remember, what we're basically doing here is we're summing, so our net area is going to equal the limit as n goes to infinity of I equals 1 to n, because remember the I is our index, tells us what rectangle number we're on. The rectangle number is what we're thinking of as I, okay? And so we're on the first rectangle, the second rectangle, and so on, and we're summing those up. And then our f of x sub I that we're putting in this case was cosecant was my function, and my x sub I was the right endpoint. And our generic one for the right endpoint, underline it up here, was that 1 plus 2 over n times I. 1 plus delta xi, a plus delta xi, that was my generic, times my width, which was 2 over n for this problem. So this is kind of how you're going to see this. I mean, it's a lot easier when I was just doing limit as n goes to infinity, sum I equals 1 to n, of leaving it as a generic function and saying f of x of I times delta x. And so what your job is to look at this and kind of say, hey, how do these things match up to each other? The first thing that you would look at is this idea of, you would recognize that the part that's here is exactly your delta x. Like working backwards, you would say delta x equals 2 over n. And that means that you know b minus a over n, so b minus a is equal to 2. Just kind of showing you how you would work back. Now that doesn't really tell me what a or b is, but it tells me that the difference between them is 2. The next thing that you would do is you would look at what's inside of here. And because that's going to identify what your right endpoint is. And in most cases, they do a right endpoint. So your x of I is going to be 1 plus 2 over ni. And so when we see that, we see the delta x here, we see the I, and so that means that this a, therefore, a is equal to 1. All right, so we get that down. And once I know a is 1 and b minus a is 2, that immediately gives you b is equal to 3. So we can kind of combine those together. Clearly, the function, you should be able to match the function up to be the cosecant on that. And then if I was writing this as a definite integral, kind of going down here, the limit of a sum becomes the integral. My a and b are 1 to 3. My function was the cosecant, and delta x becomes dx. Okay, I'm going to stop this video here and go to part 2 of the video, and we'll summarize on the next page.